My name is Carrington Kinyanjui. I am a student at the University of Manchester. I'm just completing my PhD. I am also a researcher at ILINA. ILINA is a small research group in Africa, here in Nairobi, studying AI safety and various aspects of AI safety, from technical aspects to governance aspects. And if you're interested, you can check us out. And I'm also a member of a startup working on AI applications in the continent, applications of artificial intelligence, research and development in the continent. I am going to talk, I'm not going to talk about those things. I'm going to talk about quantum mechanics, specifically its introduction. We are going to talk a little bit about the introduction of quantum mechanics and the applications, the general applications of quantum mechanics as we zero in to quantum computing and quantum communications. So let me share my slides. Just to check that you can see. Please confirm that you can see my slides when I share them. Just a moment. Can you see my slides?
Yes.
And you can see them in full screen right now. Okay, if you
Yeah.
can see them in full screen, that's fine. We will start. So today we are going to talk about quantum mechanics. I'm sure you have heard of it somehow or somewhere from someone or through videos or documentaries, or as Shannon has mentioned, through movies. Okay, it is the thing that some nerdy people do, mostly in Europe or the United States, and nowadays in China and Japan, right? And even in Africa, right? And you would like to know why it is important, okay? Why it is such an important reformulation of the way we think about our universe and the way we think about possible technologies and scientific discoveries that can come from this theory. But I'd rather call it this field, and I will just clarify that in a moment. So today we are going to talk about the basics. So why quantum mechanics became necessary, some historical foundations, the principles of quantum mechanics. These are things that physicists call postulates or assumptions, or in mathematics, the famous word is axioms, okay? So what assumptions do you need to make for you to understand quantum mechanics, or for you to be able to process quantum mechanics? We are going to talk about interpretations of quantum mechanics, and this is going to be important in us understanding why there's a difference between quantum mechanics and quantum theory, and why it is wise to just say quantum and why people just say quantum. We are going to talk a little bit about real-world applications, the future of quantum mechanics, and then the conclusion, the legacy of quantum mechanics. So we will have a short, I will present the historical foundations, the principles, and the interpretations. Then we will have a short break of 10 minutes, 15 minutes, just for any questions. And then we will proceed to applications for another 20, 30 minutes, have a final round of questions, and then some comments. So welcome, and I hope you enjoy. And I am sure, I know you've seen the videos that nobody can understand quantum mechanics. At least you will understand how to use quantum mechanics, that I promise. However, how to understand quantum mechanics, that is up to you. And you will see why it is extremely difficult to actually understand quantum mechanics. So first, I would like you to have a look at this tweet. This tweet is from September 1st, so it's very recent, from Quantum Magazine. Quantum Magazine is just basically a journal type article, newspaper or newsletter that mostly publishes interesting developments in physics, in computer science, in chemistry, mathematics, etc. But they're interested in mathematics, physics, and computer science. So please follow them on Twitter. I refuse to call it X. Please follow them on Twitter. They have very, very interesting articles. So in September 1st, just a few weeks ago, I think a week or two ago, actually a week, they published this 100-year anniversary of quantum mechanics. And you can see the first there is of a scientist called Werner Heisenberg. We will speak a little bit about him very soon, but this is a 100-year-old theory of the world. Okay, so this is an important year. Actually, this decade is going to remain important for quantum mechanics because every year there will be the 100-year anniversary of a specific discovery or development in quantum mechanics. So why is this theory so central to scientific, philosophical, and even technological developments in the century that has followed it? Okay, so it's a relatively young theory. For comparisons, Newton's theory of gravitation is around 300 years. So why is this theory so important and so revolutionary? That is what we are going to try and understand today. I'm going to make a few recommendations of books to read. This is books and media to consume, not just books. For those who don't like reading books, this is a very interesting book called Helgoland by Carlo Rovelli. I will explain why it is important. I have a copy of mine here. So Helgoland is about the history of the development and conceptualization of quantum mechanics in its early years. And you can see the very human development of quantum mechanics, debates, fights, tears, okay? Just like it is right now. There's a lot of drama, but what we have left is a very, very powerful theory of subatomic particles that we still to this day do not understand either properly or completely. So this is a nice book that I would like you to have a look at. So why quantum mechanics? Now I'd like you to transport yourself 100 and something years in the past, okay? So it's the late 1800s somewhere in Europe. We have these two theories, very powerful theories. I'll speak about them a little bit. The theory of classical mechanics, actually the model of classical mechanics. And we have another model of the world called electromagnetics, okay? Now, it is clear to people, classical mechanics deals with how bodies move in the physical world. So classical, meaning that it has been developed to deal with these specific kinds of systems, large systems. So this is the physics that you got taught in high school, for example. Newton's laws of motion, the laws of thermodynamics, etc. And we have electromagnetics developed by Maxwell and later on by other people, which deals with light. And how these two systems come to interact is through a field called thermodynamics. Thermodynamics deals with the movement of energy. You remember in your first years of learning physics or physics adjacent subjects, you were taught that physics is the study of matter and its relation to energy. And this is going to be important for the rest of our slides. Keeping this in your context window is going to be important for the rest of our slides. Okay, so we want to relate matter and energy, specifically a form of matter that we understand through the laws of classical mechanics, and energy as we understand it in the electromagnetic wave. So I'll explain this phenomenon. When you hit an object, when you touch it, it feels hot. That feeling of hot, actually, what is happening is that the body that you've hit is vibrating. Okay, this is the basic kinetic theory. The molecules and atoms are vibrating like that. So what you're feeling is that vibration. What you're feeling is the radiation from that vibration. And this radiation is what you call the electromagnetic radiation, okay? And specifically, it's infrared. So it was understood that when you heat up things, they will release this radiation, and therefore it was important for classical physicists to try tell a good story of what will happen when you keep heating that stuff, okay? When you heat it not to 100 degrees, you heat it to 1,000 degrees. So what will happen? Very soon, the laws that they had derived from looking at these objects led them to believe that they could, if you heat a substance to a sufficiently high temperature, there's a possibility that it will release infinite amounts of energy. Okay? And this is a problem in physics because physics does not deal with infinity. Okay? Infinite means uncountable. Uncountable means unmeasurable. And therefore, if you find a formula that is telling you that if I heat a piece of coal, a piece of wood, if I heat a piece of metal to a sufficient temperature, it will give me infinite energy, it is lying to you. You have not made a wonderful discovery of infinite energy. You have made a mistake. And now you need to figure out where that mistake comes from. Okay? And this was what was called the ultraviolet catastrophe. It was called the ultraviolet catastrophe because, as you can see in my image there is the visible band of light, our Roig beam, okay, the one we get taught, the light of the rainbow, for example. And then to the other side is what is called the infrared. Infra means just below, so just below the red. And ultra means just above, and this means above the violet, okay? So ultraviolet and infrared. So what happens is that they calculated and found, the classical physicists, the physicists using Newton's understanding of the world, they calculated and found that there was an ultraviolet catastrophe. That is, there are certain objects, any solid object, if you heat it to a sufficient temperature, will release infinite amounts of ultraviolet energy. Okay? And this was a failure. Actually, what was measured is more like what you see on the graph. What ended up happening is that for higher and higher temperatures, the electromagnetic radiation released would have higher and higher frequency. So this is what you're seeing it, for example, in the lower thing, 3000 Kelvin just means something like 2700 degrees Celsius. But if you heat it to 6,000, the peak of the curve shifts to the left, meaning that most radiation is released at high frequency, okay? Either visible or ultraviolet. But notice that the measured data is not infinite. It is finite. It is not infinite amounts of energy. And this was a problem. Next problem that they were resolving. Again, I want you to notice that these problems creep up when you're considering the interaction of radiation, so the stuff we talk about, light, X-rays, etc., with matter, okay? Solid objects, physical objects, okay? The interaction of energy and matter is causing these problems. And since physics is the study of matter and its relation to energy, these problems actually have to be resolved. So the second problem was very basic. When a wave comes and hits a shore, okay, if the wave is very intense, it will knock off the buildings, okay? For example, a hurricane. It has come, sadly, it has come to Mombasa in East Africa. It has come to maybe Cape Town in Southern Africa, etc. It hits the wave, it hits the city, okay? It will scatter a lot of buildings. It will scatter a lot of property. It actually causes the loss of lives, okay? So we know that intense waves with intense energy destroy or scatter more stuff. So this is our understanding of classical physics. So if you translate that to the atomic world, okay? If I heat light, an intense beam of light, I use it to heat a surface, I should expect more stuff, more particles to be scattered. Okay, so this is the story I am going with when shining intense beam of light on a specific solid, let's say. But when you do that, what you end up with is that electrons come out, but they don't come out in the numbers that you think, and they don't come out at the energies that you think. And therefore, your model of the world, this classical model of the world that uses waves to understand the scattering properties of light, is somehow wrong because it does not describe what is measured. This effect was called the photoelectric effect and was very, very problematic for a few years. Third problem. Now you have a solid, okay? You have a solid that you're trying to measure its radiative outputs, okay? When you hold someone's hand, you feel that it is warm. When you hold anything, especially on a sunny day, it's been sunny in my part of Nairobi for quite a while. When you hold the building, you feel that it is warm. The problem is when you try to measure that stuff, that warmth coming out of the building or coming out of the human being using precision instruments, you will not end up with something like what is in horizontal line 1, right? A continuous spectrum of energy. You will end up with these like lines, these very discrete and sharp lines, which tells you something about what you are seeing, okay? And there is no classical way for you to explain why you see these discrete lines, these so-called channels, rather than this continuous rich spectrum. And this introduced another problem. So we have three problems. One, that when you heat up stuff, it's supposed to give you infinite amount of radiation. Second, when you knock up solids with waves, they're supposed to give you particles proportion to the intensity of the waves, which is wrong, which is not what we see in the lab. Third, when you are measuring the radiative output of any solid or any object, you're supposed to see continuous measurements, which is also wrong. Now we have a problem. We have three wrong things. It's not even a supplementary, it's a discontinuation. You have completely failed when trying to study the interaction of electromagnetic waves with matter. You have completely failed. The model is not working. So we need to think about things a little bit differently. One of the first people to think about things a little bit differently was called Max Planck. Max Planck was a German physicist, operated at the turn of the century. So this is late 1800s to early 1900s, okay? He was a very brilliant guy. He thought, well, let us look at this first problem. The problem is that we want these solids that we are heating up to vibrate at infinite frequencies, okay? When they are vibrating like that. So the more you heat them up, the more they vibrate. The more they vibrate, the higher the frequency. So they do that instead of that, okay? And this is a story of the amount of energy inside an object. Anyway, so he said these things can vibrate, but they don't vibrate infinitely, okay? They can't vibrate at infinite frequency, at infinite speeds. There's a limit to how much they can vibrate. And because there's a limit to how much they can vibrate energetically, there's a limit to how much stuff they can emit, okay? There's a limit to the energy of the stuff they can emit. And how we do that is by making the vibrations discrete and by making the frequencies that are released into the wild, into the environment, also discrete, meaning that there's no smaller chunk of energy that you can receive more than this, i.e. there's no bigger vibration that you can have more than this. So he called these things quanta, these discrete chunks of energy that you cannot go below. He called them quanta. Because you have a limit to how low you can go, you have a limit to how much stuff you can release. If you can go infinitely low, then you can release an infinite number of stuff. But if you cannot go infinitely low, if they're discrete steps, for example, then the stairs is countable. It can be a lot, but the number of steps that you have to take to get to the second floor is countable because of this, and you can predict this. And this was what was called quanta. And for most people, this is the birth of quantum mechanics. This is the ultimate birth of quantum mechanics. But he himself did not recognize this as a physical theory. Okay, so that's why some people dispute this as the birth of quantum mechanics. He thought he was playing mathematical tricks on formulas so that to make sure that the curves that come out of the formula match the data that we see in our laboratories and engineering experiments. So that is what he called quanta. He said that the energy of any system comes from is related to its frequency. And this sort of makes sense, especially for radiation, okay? So higher frequency means that it is doing much more. And if it is doing much more, it has more energy, okay? So lower frequency means it's doing less, and therefore it has less energy. But he related this to H, which is called a constant and has now been called Planck's constant. So that's the first thing. He has said that these things come more like sand particles rather than sea waves, okay? It's more like sand particles rather than sea waves. His friend and the more famous physicist, Albert Einstein, suggested that we should apply his conceptualization, Planck's conceptualization of the particle, we should apply that also to this problem. Instead of thinking of waves hitting these electrons, we should think of particles, single particles hitting these particles and releasing them. So if you think about it that way, it makes a little bit more sense. So if the particle has a lot of energy, okay, a single particle can eject 5 small particles, okay? But if it has low energy, it doesn't matter how many particles you have. It is not going to move anything. It is like trying to slap a giant or trying to slap a tree. It doesn't matter how intense your slap is, the tree is not going to fall because you've slapped it. However, if you have something like a tractor, you can knock off the tree because the tractor has more energy. So Einstein suggested that this Planck's formulation of quanta at very, very high energies is what ejects particles from solids. And this is what is called the photoelectric effect. So Planck's idea of the quanta moves from being a mathematical idea that a physicist has invented to fit the data, it becomes a real physical object, that there actually are discrete units, countable units of energy. And we can prove that. Why? We can prove that because we see it in this photoelectric effect. So again, this is one very important paper. And in fact, this is the paper that gave Einstein his Nobel Prize in physics, and it is not his work, for those of you who are familiar, it is not his work in relativity. It is his work in quantum mechanics that gave him the Nobel Prize. Now we have a problem. We know from engineering and previous physics that light is a wave. But Einstein has proven that physically, not colloquially, but physically, light is a particle. Okay? So we have to find a way of resolving this. Is light a wave? Is light a particle? Okay? Keep that in your mind for the coming slide. Next piece of progress was Bohr, Niels Bohr. Niels Bohr was a Dutch physicist, another friend of Einstein. So as you will notice, the physics community right now is quite small. The physics community working on these problems of the interaction of matter and energy is quite small. So they know each other and they're friends. So Niels Bohr basically applied Planck's and Einstein's ideas to visualize the hydrogen atom and any other atoms. So he said that basically we have a central nucleus and we have electrons which are negatively charged orbiting the nucleus. They're able to orbit the nucleus because the nucleus is positive. So the electron is attracted to the center, but because it is also attracted to the center and moving to the side, it ends up moving in a circle. So that makes sense like this. The electron is trying to move in a straight line. This is the classical law, the first law of inertia, but there's a nucleus with a positive charge. So it keeps on being tried to be pulled to the center, but it wants to move in its straight line. So it is trapped in an orbit like that. Niels Bohr said that there are only a set of discrete allowed orbits. It can't move at any random distance from the nucleus. It needs to move at these discrete orbits. And to move between these discrete orbits, it needs to give out or absorb a unit of energy. And I hope you can now remember Planck with his quanta of energy. So to move between orbit 3 and orbit 2, it will release a specific amount of energy. For it to jump from orbit 2 to orbit 3, it needs to absorb the same unit of energy. And therefore, especially when interacting with matter, radiative energy becomes discrete, becomes quantum. Okay? Now, this is an important discovery. It is a reformulation of the way we think about atomic physics. And because of this, Bohr got a Nobel Prize. Now, we are still with the problem of, is light a particle or is it a wave? We need to find a way of resolving that. Another physicist, by the way, I hope you can see that I put this picture of Einstein as a young fella deliberately. Einstein was working on the photoelectric effect, I think when he was 25 or 26. Okay, so if you're 25 or 26, your days for doing physics are already over. So he resolved this problem in his 20s. And also Louis de Broglie actually resolved this problem, I think, when 24. Okay, these are very, very young people thinking about very, very new ideas, as is generally the case. So anyway, Louis de Broglie starts to think about this thing a little bit abstractly, and he says, why do we want to be forced to choose between particles or waves? Why can't it be both? And he started writing his PhD thesis with that assumption that these objects, not just light, but also matter, can be both waves and particles. Okay, and he wrote a very simple formula, and that's why I wanted to show it. There it is. Lambda is equals to h over p. Lambda is the wavelength. The wavelength is just the distance between two successive peaks of a wave. Okay, that's called a wavelength. P is momentum. H is this ghost here. H is this Planck's constant here. Okay, so de Broglie is relating a wave, okay, lambda, the property of a wave, to P, the momentum, a property of a particle, and saying that these two things are essentially the same thing. And that's a very, very interesting discovery. It then tells you that anything that has a momentum, P, has a wavelength, therefore is a wave, and vice versa. Anything that has a wavelength has a P, is a momentum, therefore has particle properties. And therefore the implication follows that any physical object that you measure has both wave-like and particle properties because it is both things at the same time. And this is one of the most counterintuitive properties of quantum mechanics. Now, this looks silly until you go and actually measure it in the lab. There are material scientists in Kenya who rely on this idea to do their work. The physicists around the world doing different things who rely on this idea that an electron can have a wavelength and light can have momentum to do their work. And I give an example of this in the slides here. So what you are seeing here is the measuring of the properties of crystals. You can see the very, very bright spots are arranged in an orderly manner. This is because this is a crystal with evenly spaced out atoms. But I want you to see that the spots are not completely sharp. They are blurry at the edges. And this being blurry at the edges is the result of is usually associated with wave reflections rather than particle reflections. Particle reflections are meant to be sharp. So as you can see in this physical image of actual physics, both properties are existing at the same time from the measurement of electrons. Another very interesting experiment that you could then use to prove this is the double slit experiment. Okay, so double slit experiment is very simple. You have a barrier. So there is the screen. Okay, the screen is that yellow bar with the two gaps between it. If you throw sand particles at this screen, you expect to see like two basic concentrations of your sand particles at the optical screen, at the background. Okay? However, when you do it using waves, what you expect to see is more like this pattern. Can I ask the person with their mic on to switch it off, please? Switch off your mix so that, please, silence your microphone, please. Or admin, please silence the microphone for me. When you hit it with waves, what ends up happening is you form this very beautiful pattern of waves interacting with each other and canceling each other out or amplifying each other. And this will form something called an interference pattern, where there will be several lines rather than just two lines. So let's do this with electrons. Let's do this with atoms to find out, or molecules, to find out whether particle is a wave. These things are waves or particles, okay? So let's carry out the experiment. When you carry out the experiment, okay, you will find that these systems, a single atom thrown one at a time at these slits, will end up with the pattern of a wave and not the pattern of your sand particles, okay? You will see this interference pattern, okay? And then if you try to open this gap at D, capital D up there, to try to see the experiment as it is going on, there is a collapse. You will see the two patterns rather than the one pattern. So this introduces this concept that it is both particle and wave at the same time. Final experiment, the Stern-Gerlach experiment.
Just come in.
Sorry, there's someone. Could you please switch off your microphone, please? Can I request that you switch off your microphone?
Vanessa, please switch off your mic. Sorry for that.
Okay, let me go back. Sorry. Let me find my slides. Sorry about that. Can you see my slides?
Yes.
Okay. So the final experiment that I think is very important is called the Stern-Gerlach experiment. Here, you place a beam of charged particles in a magnetic field. So this is just a big magnet, the north and south. I hope you can see the north and south between the magnet. And then you're just basically sending silver atoms, it could be anything, between this field. From classical physics, you expect to see a continuous distribution, a sort of scattering of particles from one end to the other end of the screen that you're using to measure. However, when they carried out this experiment in 1922, they found that there were only two spots, up and down, okay, corresponding to alignments of the particles. Some theorists then concluded that there is a specific angular momentum of these particles, and this angular momentum corresponds to an orientation towards the y-axis. For example, if you're measuring the y-axis, there's only an orientation of up and an orientation of down, and there's nothing in between. And this is what is resulting in those two spots instead of a continuous sort of scattering in the screen. And this is one of the most important experiments of quantum mechanics because it led to the inference of the existence of this thing called spin. And spin is important because it then allows us to study how to control these particles, okay? So spin is a form of angular momentum. Angular momentum is a momentum that exists in bodies that are moving in circular orbits or circular type orbits. Now, we needed to completely reconceptualize the way we understand physics because of these experiments that we have seen, right? And these observations, these theoretical observations proposed by Planck, proposed by Einstein, proposed by Niels Bohr, proposed by Louis de Broglie, and these experiments that we have just spoken of, the double slit experiment and the Stern-Gerlach experiment. So what would such a theory look like? What would such a model of the world look like for it to be able to explain all of this stuff that we have just seen? So let us look at the structure of this theory, the things that you need to surrender in order to understand how to explain these puzzles or experiments. The first thing is superposition. Superposition is a very simple idea when you're looking at waves especially, that something can be in several places at the same time. Something can exist in several states at the same time. Now, this is very intuitive for waves, okay? So a wave is something that looks like that, okay? Sure. Let me show it. Let me just show the example of a wave so that a good example of a wave, an example of a wave is this thing, okay? So a wave can have different frequencies at different points. It can have different energies at different points. It can have different heights, the amplitude of the wave at different points. So the first thing is superposition. This idea that a single system can have several properties, okay? Another good example is, I don't know, a country. Nairobi can have different properties at different points. There's some parts of Nairobi which are safe. There's some parts of Nairobi city which are not. So Nairobi is in a superposition of safe and unsafe states, okay? So that sort of makes sense for large systems and makes sense for waves. The second thing is the uncertainty principle. And the third thing is the wave-particle duality. The uncertainty principle is the idea that you cannot measure objects at the same time. The third thing is the wave-particle duality that we have just spoken about it here, right? That particles or any systems can exist at both wave and particle properties. And the last thing is that it is inherently probabilistic. That is, you cannot speak usefully because of the uncertainty and because of superposition. You cannot speak usefully about this particle. I am sure that it has these properties. This will fail. Now, how do we put that into mathematics? Remember, physics is a combination of the study of matter and its relation to energy. How do you encode the relationship between energy and matter mathematically? Erwin Schrödinger, who is an Austrian physicist, Austria was a country separate from Germany before the wars. Erwin Schrödinger came up with something called the Schrödinger equation. And whenever students meet this equation, they get worried, but I would like to go through it very, very quickly. We have said physics is the study of matter and its relation to energy. So the first line you're seeing is the total energy of a system. H is equals to T plus V. So T is kinetic energy, V is potential energy. So what you're trying to say, the total energy of a system or a body is its kinetic and its potential energy. The energy that it has because of existing, of just moving around, its internal energy, and the energy that it has because of being in a system. For example, because I'm in the second floor of a building, if my floor disappears, I will fall down and break my legs, okay? So I have high potential energy because I'm in the second floor. But I also have kinetic energy because I'm maybe moving around my arms. So Schrödinger created a similar equation for quantum systems. And the quantum system is this, okay? So the first thing I want you to pay attention to is the fork-like thing outside the brackets that is called the wave function. The wave function or the state vector, okay? And what you're doing is trying to ask the state vector certain questions and have it answer your questions. So the things inside there are called operators. Operators are the things that will help you answer your question. The first complicated one with a negative is called the kinetic energy operator. The second one is called the potential energy operator. So if I apply these kinetic energy operators and the potential energy operator to this thing called the wave function, it will give me all energies that I can measure in that quantum system. So it is a very important equation because it relates energy, which is the H, to matter, okay? Matter comes in several forms. One is its kinetic energy. So it is the M that you're seeing, M for mass, and also the potential energy. So applying this Schrödinger equation, you don't end up with this thing that Bohr talked about. The Bohr model had its limitation. You end up with something like this, okay? Something very rich and beautiful. And these things are called orbitals. Orbitals are sophisticated versions of the energy levels you studied in chemistry class, okay? So I hope you can see that they look like clouds rather than specific discrete lines. So this cloudy behavior is essentially the probabilities that are derived from carrying out measurements guided by this Schrödinger equation. An important thing to pay attention to is that there are four numbers you need to pay attention to. One is called your principal quantum number. This is the energy levels you heard of in chemistry, okay? So these energy levels that are here in Bohr's model, these lines, okay? So a particle at orbit 3 has higher energy levels than a particle at orbit 1. Say another quantum number, sorry, let me go back. Another quantum number is angular momentum. And the third quantum number is the magnetic, the orbital orientation, which determines the shape of the orbit, okay? And then the spin that we have spoken about. The reason why you were forced to write 2882 in your chemistry classes in early high school is because of something called the Pauli exclusion principle, okay? So particles, especially electrons, cannot occupy the same quantum state. And same quantum state means here having the same quantum numbers. And therefore, because they cannot fit into the same quantum state, you have to pack them in a certain manner. And that is why you are forced to do this 2882 thing. Quantum tunneling. Another important effect is that these systems, because they're in a superposition of states and there's an uncertainty as to where they are able to basically traverse energy barriers. A simple example of an energy barrier is a wall. So these systems have a small but finite probability of existing outside these energy barriers. And it has a lot of important implications for industry. For example, the creation of tunnel diodes, the building of scanning tunneling microscopes, these high precision microscopes. It has importance for nuclear fusion. I'll explain this a little bit. When you're trying to collide two nuclei together, which are positively charged, the positive charges causes this nuclei to repel, to try and move away from each other. However, because of quantum tunneling, there's a possibility that this nuclei can basically tunnel into each other and basically collapse into each other and cause something we call nuclear fusion. So the sun that you're seeing in the sky right now, if it's day in your part of the world, is a result, is partially works because of quantum tunneling. Another important result is quantum entanglement. This is where particles that even could be physically separated from each other, right? They're very, very far from each other, are understood in quantum mechanics to be the same object. That is, they share the same quantum state, okay? And because they are understood to be the same object, the measurements that you carry out in this part of the object will affect the measurements that you carry out in this other part of the object. And this is important. So what ends up happening is that you affect this object by the measurements you carry out in this object. And Einstein, although who was involved early in quantum mechanics, rejected this idea because it seemed to be inconsistent with his understanding of physics. And this is what is called spooky action at a distance, okay? i.e. that the effects of measuring this object propagate to that other object at faster than the speed of light. And this is problematic. However, there have been a lot of studies, theoretical and experimental, that have led us to first conclude that this phenomenon actually exists, and second, it does not violate the laws of physics. And if someone is interested to understand this in a little bit more detail, please ask me the question after. Now, interpretations of quantum mechanics. Remember that I'm talking about quantum mechanics, rather than quantum theory. There's a reason for this. And I will tell you my understanding of the reason for this. For you to be able to say that you have developed a theory, it is not enough to supply equations. You must explain to other scientists, reviewers, conference participants, what stories these equations, these very sophisticated equations, tell about the world, okay? So this psi thing that we are seeing here, this fork thing, right? The wave function, what is it actually? These operators, what are they actually? What do they correspond to in the physical world? Okay? The combination of mathematics and a story of the world is what is called a theory. Now, the problem with quantum mechanics is that it has several stories of what is going on in the world, in addition to the equations. And this is why people say that it is that it is impossible. Or if someone tells you that they have understood quantum mechanics, this is Feynman's quote, that they are lying to you, okay? It is because the stories that we tell, the stories, the interpretations that we make of the equations and the measurements we are making are very, very different and are all consistent. Okay, so quantum mechanics has something called an interpretational problem. That is, there are many equivalent interpretations of quantum mechanics. The first one, and most popular, and was one of the first, is called the Copenhagen interpretation. The Copenhagen interpretation, because the people who initially worked at it were in Copenhagen. Copenhagen is the home city of Niels Bohr, one of the most influential physicists of his time, alongside Einstein. Basically, the idea is that the wave function is something mathematical, and it can collapse when you carry out measurements. And this is why the double slit experiment works the way it does. that this mathematical thing, when you try to measure it, will collapse into a single state and basically become particulate. It will become a particle. And Copenhagen interpretation comes out of a culture of, I would say, of engineering. Don't ask too many questions of why quantum mechanics works. Ask a lot of questions of how it works. Okay? The important thing is, what can I use this system, this model of the world to do? The many worlds interpretation rejects this philosophy and also rejects this idea that this wave function and these operators are not physical things. It says, no, 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 no. Quantum mechanics is talking about actual waves, okay? And these waves correspond to possible states in separate universes, essentially. No. During the superposition, they are in the same universe. But when you carry out the measurement, the wave function does not collapse. What happens is that universes separate like that. And if you're interested in knowing the details about this, also ask me in the questions. So they separate out like this, such that two observers exist. One observes the particle being in that state, and the other observes the particle being in that state, okay? And because of this, the many worlds interpretation rejects the possibility of collapse of the wave function. There's another more physical theory which adds more stuff to the Schrodinger equation. It adds something called a pilot wave. And literally the pilot wave, its job is to pilot the particles, okay? And to pilot the wave function. And what it does is to guide the movement of these particles and these quantum systems that we are seeing. However, you cannot measure the pilot wave directly. And therefore, this pilot wave is normally sometimes referred to as belonging to a class of things called hidden variable theories. And these hidden variable theories basically have extra numbers, extra objects that cannot be measured, that explains the things we measure in the lab. The last one is not a full interpretation, but quantum decoherence basically says that quantum mechanics fails or doesn't fail, reduces to the classical theory because when we add more and more stuff, there's more and more noise, essentially, and this more and more noise essentially causes these quantum properties to disappear. And this will be important for quantum computing in the summit. Anyway, 100 years, nobody knows which interpretation is correct, and we are essentially stuck, and we cannot tell the difference between these four. Most physicists do their work assuming that this is not a problem, and actually you can be very effective doing your work without interpreting quantum mechanics, trying to build a quantum theory. You can be very effective, just like you can be very effective with using your mobile phone without knowing what is going on inside, what is a semiconductor, etc. You don't need to know these things. You just need to use your mobile phone. So you can use your quantum mechanics without necessarily understanding it. So I will take a short 5-minute break, although we are very late. We also started, I think, 20 minutes late. I will take a 5-minute break for questions, and then we will proceed with applications. That will be a 10 to 15-minute presentation. 5-minute break. Any questions so far to do with the introduction and interpretations and conceptual foundations of quantum mechanics? Any questions in the chat? Any questions? Raise your hand. You can raise your hand and then ask a question. And then we will continue at around let me target 4:10. So one question, please. One question in the chat. Don't be shy. Don't be shy. I can see there's a question in the although the person has, oh, this is a different one. I can see there's a question in the chat. However, where exactly is the transition point between quantum and classical behavior? Wycliffe, that is a very, very good question. Sorry, I've muted myself foolishly. I've muted myself foolishly, sorry. The transition between quantum and classical depends again on interpretations. Let me explain what I mean. There is an interpretation of quantum theory or a way of viewing quantum theory in which you recast it as a universal theory. A universal theory means that it is a theory or a model of the world that applies at all scales, at all times, at all energies. Therefore, it is a universal theory. Okay? Niels Bohr, Werner Heisenberg, we haven't spoken about Werner Heisenberg in detail, maybe we will at some point, developed something called a correspondence principle. A correspondence principle starts with quantum mechanical objects, then ramps up the energy, ramps up the mass, and ramps up the number of particles that you're dealing with. When you ramp these things up, they showed that essentially the formulas of quantum mechanics become exactly the formulas of Newton and become exactly, therefore, the formulas of classical mechanics. And what that means is that, according to them, according to the way they understood this 100 odd years ago, is that classical mechanics is a special type of quantum mechanics that we interact with because of the scale of because of our sizes, because of our masses, because of our etc, etc. However, what is really happening is that quantum mechanics is in operation with classical mechanics as an approximation. And you can derive very, very roughly equivalent ways of moving between quantum mechanics and classical. Now, this depends on the system. Sometimes it's, for example, for molecules, you could find that it is a few million molecules, and then it becomes ineffective to do quantum mechanics. It becomes more effective to do classical. Sometimes it's just adding a few things. Sometimes it is just making a measurement on these objects using a classical instrument results in the particles becoming classical. Okay, so it really depends on the context. However, there are other interpretations which disagree with this correspondence principle. Okay, another question. Just one more question. Somebody, I want to hear someone else's voice. I don't like hearing myself speak. Somebody raise your hand and ask a question directly to me, please. Don't be shy. You know, the beautiful thing about quantum mechanics is nobody understands it completely or nobody understands it at all. So you can ask a question that you think is foolish, and actually it is a very, very deep question that is worthy of research. So please ask a question. Yes, Semaganda. I would suspect from Uganda, but you can introduce yourself. Ask.
Thank you, Carrington. Hi, how are you? George, yeah.
Did we meet?
Of course, I think we've met
Yes.
earlier.
Yes.
In Abachigali. Good to see you again. Yeah, mine is really going to be a quick one because I'm a physicist and a tech person, but actually the class is quite tricky and complex for me personally. So now I'm thinking about my Ugandan community that has joined in this call on how they are struggling to catch up and to understand the basics, as you said, for the lecture. But maybe for the lectures, because we are looking now on the several ways on how we can collaborate with Quantum Kenya, Quantum Uganda, and Quantum Africa at large on how we can have these classes a bit. I don't know how we can push them a bit to a lower level of understanding for beginners, because literally the community that is in Uganda is fully beginner. And I don't know, maybe we can have this discussion off the call and we see how best you can come in and support. Yeah, yeah. Thank you so much.
Thank you very much. First, for those people who have just met quantum mechanics today, please, please, please don't run away. The problem is that you do not come to understand. I don't think I understand quantum mechanics. I am used to quantum mechanics. In Swahili, there's a word called zoea. Zoea hiyo. Just get used to it. So the more you do it, the more you practice, the more you read, the better, the more you get used to it. So quantum mechanics is very weird because it is unintuitive. It does not rely on your intuition. It relies on your ability to logically understand how A flows from B. It relies on that ability. And actually, this is probably the simplest. It can be made simpler, but it can be made simpler at the loss of information. So if we try to make it much more simple, it will essentially confuse matters rather than make it clearer. However, I would suggest something like this. There's a possibility of breaking bits of this so that we can, like, slide 1 to 5 can be expanded into 20 slides. Okay, and this will make some of the stuff a little bit more clear. But I would encourage you to just keep on reading, keep on watching YouTube videos, keep on doing this so that you get used to the theory rather than to understand it. Yeah. But thank you very much, George. Nice to see you again. There's one question and then we go back to the class. Is modern physics the same as quantum mechanics? We will talk about this towards the end. Quantum mechanics is part of modern physics. There are other things in modern physics, like, for example, the theory of relativity or the special and general theories of relativity. There's an application of quantum mechanics to a new field called particle physics, application to nuclear physics. We are going to talk about this too here. So there are several aspects of modern physics, okay? What is considered modern physics? All of these things are modern physics, with quantum mechanics being one of them. Okay, quantum, somebody missed the first part. Quantum is basically a discrete unit of any object. So the quantum of a society is a person. The quantum of the beach is the sand, is a sand particle. So any discrete unit of something is called a quantum. Have I explained like you're a 5-year-old? I hope so. So I'll go back to sharing my slides very quickly so that we can finish the class so that I don't keep you here too long. So applications of quantum mechanics, the first and most famous is nuclear physics, okay? So just 10 or 20 years after quantum mechanics was fleshed out in its full form, the nuclear bombs were exploded over Hiroshima and Nagasaki. Just 20 years. So this theory, this reconceptualization of matter became immediately important to geopolitics very, very fast. It was actually pretty fast, considering the move from science to technology. The traditional applications of science in technology, this was relatively fast. First, it was understood that essentially the nucleus itself could have energy levels very similar to the energy levels of electrons, okay? The way we have talked about energy levels of electrons being at one state or another state or another state or another state, you could essentially do the same for the nucleus. Now, these energy levels were called magic numbers, just like we spoke about quantum numbers, okay? And then the decay of this nucleus is governed by quantum mechanics, just the same way the electron moves from this state to this state and emits some light. Similarly, nuclei, very many nucleuses, basically the plural of nuclei, can have a high energy or lower energy, and this is governed by quantum mechanics. And then tunneling, as we have said, enables nuclear fusion. Nuclear fusion is the coming together of nuclei, okay? Nuclear fission is the splitting of nuclei. And this is an example in my picture. So a neutron knocks a nucleus. The nucleus becomes unstable because the energy has gone to an unstable state, and therefore it needs to release a lot of energy spontaneously. And this is what happens in stage 3. The energy essentially results in the splitting of the nucleus into 2 separate objects. For example, in the case of atomic weapons, it's normally uranium is bombarded by a neutron, and then it splits into barium and krypton and releases 3 extra neutrons. And this is the process of nuclear fission. Fission is splitting, fusion is joining, okay? And this is the basis of nuclear reactors. Anytime you hear about nuclear reactors, they are operating on the basis of quantum mechanics. And nuclear medicine, there's a new field, it's not that new, but there's a field of interaction of nuclear physics and medicine called nuclear medicine. If you have heard of PET scans, these are positron emission tomography scans, radiation therapy when you're dealing with cancer, right? All of this operates on the basis of nuclear physics and therefore of quantum mechanics. Oh, just a quick break. If you have not watched this movie called Oppenheimer, please watch this. It is a very good depiction of how quickly quantum mechanics was applied to the building and construction of nuclear physics and therefore of the atomic bomb, okay? There's a less known series, it's less famous, but it is just as good, called Manhattan, okay? The construction of the atomic bomb. It talks about basically a dramatization of the lives of the physicists and the families of these physicists as they were constructing this bomb. So these are important movie recommendations for you. Please have a look. There's another theory called quantum field theory. Quantum field theory essentially deals with the applications of quantum mechanics to understanding the properties of matter in a very similar manner to chemistry. And that is why I have this table called, you can call it the periodic table of particles. I will explain it. So essentially what you're trying to do here is, given this very strange theory called quantum theory, can I essentially use it to understand light? Can I use it to understand protons? Can I use it to understand neutrons, etc.? If I can apply this understanding to these systems, I will have constructed something called quantum field theory. It starts with this idea of the field, but not the field in the sense of the electromagnetic field, the field in the sense of a quantum field. And then it says all particles are just excitations of this field, okay? Sort of like the way you can jump into a pool and cause some droplets of water to splash out of the pool. So when you hit a quantum field, what comes out is a particle. So for example, when you hit an electron field, what will come out is an electron. And when you hit an electromagnetic field, what will come out is a photon. And that way you can construct the entire universe using quantum fields. So there are several particles here. I won't get into the details. If somebody is interested, I will leave my email and my WhatsApp number. We can have a chat about this later on. But things that you might care about now, semiconductors, okay? So quantum mechanics not only explains, but also models, and it predicts the behavior of electrons in solids. So therefore, if I want to build a semiconductor chip, and the smaller and smaller I want to make this chip, the more and more attention I need to pay to quantum mechanics. You can call this something like the reverse correspondence principle. So because of these transistors, okay,
Stima iko imepotea?
right?
Sijaona hata imepotea.
Transistors, diodes.
Silirudi jana.
Please mute, Barbara. Barbara, please mute. Transistors, diodes, and lasers. In fact, lasers means light amplification by the stimulated emission of radiation. And it works basically on the basis of this principle outlined by Bohr. You can essentially coordinate using electromagnetic fields how electrons in atoms go up and lower in energy levels. And if you coordinate this, they're going to release light in a coordinated manner. And therefore, it will be very, very intense. And because it will be very, very intense, it will be amplified. And therefore, this principle of light amplification by the stimulated emission of radiation. Solar cells work using the photoelectric effect, right? The sun shines on this solid. It ejects electrons at a certain energy level. These electrons are basically channeled into a system and they end up charging. Moving charged particles is what you call a current, and therefore it ends up charging batteries, and you can store that energy, etc., okay, in a capacitor. So I hope you can see a lot of the stuff that we take for granted, including your laptop, works on the basis of quantum mechanics already. So technically, I just want to be stubborn here. You already have a quantum computer if you are trying to think about whether my computer uses quantum mechanics. But we all know that a quantum computer is a very, very different beast. So quantum computing. I will speak a little bit about computing theory, but please don't lose me. Don't switch off. I will speak about it for just 1 minute. Computing is the process of how do I represent information using discrete units, okay? I want to build a house. How do I arrange my stones so that it doesn't end up as a church, doesn't end up as a dining hall? How can it end up as a house, okay? And this is the central problem of computing. How do I arrange very basic units of information in a manner that they are useful? And these basic units of information are called bits, okay? The ones and zeros you keep hearing. And carrying out computation on these bits of information is essentially rearranging them so that you get a result out of this rearranging. And the process of rearranging these bits is what people call computing. Okay? That is basically computer science 101. Okay. The issue is that for me to represent a sufficiently complicated state, like to represent the state of a laptop, I cannot do it using 1 bit. 1 bit of data is very, very simple. It cannot represent a complicated thing such as my laptop. So what do? I find very, very many bits. And because of the process, just like if you have 1,000 socks, all of different colors, sorting them out is very difficult. The process of rearranging very, very many bits is also very difficult. Therefore, carrying out computation on large data sets is difficult for that reason, okay? The process of rearranging and moving around and manipulating these bits becomes complicated. That's why scaling anything in computer science is difficult because of this problem of numbers. Okay, now, but quantum mechanics has told us something very, very strange. It has told us a single thing can be in several states at the same time. Superposition. A single thing can be in several steps at the same time. This principle of superposition. Therefore, I can have a single thing which I can manipulate as a single thing, and yet it is carrying out the information processes of multiple things. And this thing that I can use to represent several bits is called a quantum bit. That is a bit that is in superposition of several states. And therefore, it follows, my ability to rearrange this single bit will be highly, highly simplified compared to my ability of arranging 1,000 classical bits. And therefore, the process of computation of a quantum bit, if I can stabilize the given quantum bit, is much, much simpler. And therefore, it implies that quantum computing offers the possibility of carrying out complex computation at a much, much faster scale compared to classical computation. And this is the idea of quantum computing in summary. Now, it looks beautiful. It looks very attractive. But once you get into the details, they become very nasty very fast. First are engineering problems. What thing am I going to use to represent the bit? In the case of classical, we have this transistor. Although it's a quantum system, it is representing a classical bit. It's either on or off. And on is 1, off is 0, blah, blah, blah. Now I just need many transistors and I can carry out my computation. I just need many bricks, like that single transistor brick, and then I can build my house. But here you have to make decisions about how you represent your quantum bit. Do I use photons? Photons are units of light, quanta of light. Do I use electrons? Do I use superconducting circuits? Right? So that is the first problem. And the choice you make here has implications for the engineering complexity of what you do. Second thing, I need to make sure that this system has preserved quantum properties, okay? Is not moving around randomly, because if it is moving around randomly, it will introduce noise. And as we have said from the correspondence principle, if you have too many atoms, if you have too many quantum particles interacting, they will collapse into a single state. They will become classical. And if they become classical, you do not have quantum bits, you have bits. And therefore, there is no advantage. Actually, mostly you just have noise. You don't even have bits. You just have noise, although you have some information. And therefore, you have a problem of how to preserve these states in quantum, so that they can keep their quantum properties, and then you have qubits, and then now you can carry out your quantum computation. This is the problem of maintaining coherence, maintaining the quantum properties of this system. And it is a major unsolved technical challenge in all forms of quantum computers. And this is why when you scale qubits, it also becomes a problem. How to maintain this property becomes a problem. However, what is the potential? If we were able to build these quantum computers at scale, and people are working desperately on this, what could we do with it? There are two things that are very important in computer science. I will start with the second and then move to the first. The second is called search. Such is a very important basic idea in computation. Such is the process of how do I find a solution to a problem? How do I find an answer to something? For example, I am the CEO of Jumia. I have received 50,000 orders today. I need to find a way of optimizing my delivery schedule such that I don't waste money and I don't waste the customer's time. This is called an optimization problem. How do I move 10,000 objects to 10,000 different households in a manner that saves time? Okay, this is an optimization problem. And you solve optimization problems. Another good one is traffic. Okay, so your Google Maps recommender uses optimization algorithms to tell you which route is best to take at what time. Okay, so all of these are optimization problem. If I type in my Google search box, is the answer I'm going to receive relevant? That is another optimization problem. All of these optimization problems are solved using search. Okay, and search is the question of how can I quickly move through very many million wrong answers, usually called suboptimal, to find the one correct answer that makes sense for me, the optimal answer, the optimal option. Okay, optimizing. It has been found that quantum mechanics can help you do this thing. It can help you do search. And this is quantum search, and quantum search through something called Grover's algorithm. It's not very old. It was developed in 1996. Essentially, what you do is make sure that your answer is in a quantum state that is opposite to all other wrong answers. And then you just carry out that measurement. And it does this automatically because of this ability of being in multiple states at the same time. There's another important thing in computing called encryption. Encryption is how I can make sure that I am speaking to you over the internet and nobody is going to hack my message and make my message more complicated than it already is. And I'm sorry for that. Encryption is how I protect communication over the internet, okay? How I encrypt information so that anyone who wants to steal this information struggles to decrypt it and find the information, okay? Emails, financial transactions, etc. Your Twitter account is also encrypted. It has been found that there is an algorithm called Shor's algorithm that can essentially attack the central piece of mathematics that is behind most encryption schemes today. And this algorithm can essentially help anyone with a quantum computer attack most encryption schemes that are in existence. Okay, so using a quantum computer, there is the possibility of me being able to read anyone's email. There's the possibility of me being able to read anyone's tweet or anyone's DMs, okay? And this is such an important implication of this system. The algorithm is called Shor's algorithm. It especially deals with something called prime number factorization or just factorization. Proteins, particles in material science, etc., are quantum particles. For you to simulate a quantum system using classical algorithms, you have to have much more computational facility than you need to simulate a quantum system using another quantum system. And therefore, if we can reduce something called the computational complexity of simulating these systems, because we have quantum computers, it could promise, I don't want to be like a snake oil salesman here, it could promise rapid discoveries in drug, rapid discoveries in biology, rapid discoveries in material science development. And therefore, this is also an important application of quantum mechanics. But all this will be discussed in detail in the coming sessions. Just to conclude, quantum mechanics is an important theory that has basically underwritten the last 100 years of technological and scientific development, especially in physics. The next 100 years could see something like that for computing. As important a change in the way we think about computing and in the way we think about digital communications. Okay? It has helped us resolve paradoxes, as we have seen, that classical physics couldn't explain, and we still don't understand it, but it is our most successful physical theory. Successful meaning it explains a wide diversity of things that we see in the physical world, and it also helps develop a wide diversity of technologies. So what is going to come in the future? I honestly don't know. I think quantum computing is going to be important. High energy physics is going to be important, but I guess we will see. So thank you very much. Thank you for being patient with me. We will go to questions. Any questions in the chat? 2 or 3, and then I will hand over back to Shannon. Thank you. Any questions? Yes, Kevin.
Hello, thank you for, can you hear me? Okay, thank you for your presentation. It's really insightful, but I was wondering then, at least according to your experience so far, how have you interacted with like different interpretations of quantum mechanics, especially how they handle like the transition from a superposition to more definite states? And in the same breath, if you can, I'm wondering what you think or how we ought to approach physics education, and also what we need to sort of analyze about our interactions with observation or experimentation. So would we need to now, for example, move from observations that say tend to look for definite outcomes, or deterministic sort of approaches to something that's more question mark, something like that? Yeah, I hope I've made sense.
Thank you, Ogeto. Nice to hear your voice. I did not know that you are the Ogeto I knew, so nice to hear your voice. First, interpretations. So, what stories are we telling of the physical world, especially when it comes to superposition? Now, how do various interpretations of quantum mechanics talk about superposition? This comes from, essentially, what stories do these interpretations of quantum mechanics tell of the wave function, this psi thing, okay? If you tell a story, and this is, I didn't want to complicate the explanation, but I have to. This is a problem called the ontological status of the wave function. If you tell ontology is just what is there, and epistemology is what we observe, okay? So if you think that the wave function is not an invention of human beings, that it is a physical thing, and when we write it in our equations, we are talking about a physical object that is actually out there in the world, okay? It has implications for what you think a superposition is. This is called the realist position. The realist position basically says something like this: this wave function is real, And therefore, the superposition of these states are real. An example of a realist interpretation is the many worlds interpretation. It essentially says that actually what is happening is that this electron is in a superposition of being at this energy level and this energy level. It is actually real. And therefore, your observation results in a splitting of the universe such that you, Ogeto 1 will measure this electron being in this state, and Ogeto 2 will measure this electron in this state. That is one way of looking at this thing. So therefore, the superposition is real, and the result of carrying out measurements on a superposed state are also real. There is no disappearance. There's another way of looking at this in which the quantum particle is known, the wave function or this state vector, the wave function is not real, is a mathematical thing. The way Planck talked about his quanta, the wave function is a mathematical thing which we are using to describe quantum particles. This is called the positivist interpretation. An example of a positivist interpretation is the Copenhagen interpretation. What you're doing here is essentially saying, okay, this thing is not real. Therefore, it is not an important question to ask whether this particle is actually here or here. The important question is, if I point a torch at this particle, where am I going to see it? Because that is the thing I'm going to record. Whatever stories quantum mechanics is telling in the back end is not important to me. The important thing is what I am seeing on my screen. The semiconductors, the buses, whatever, all this stuff that is happening inside my laptop is useless to me. The important thing is whether I can open my email. So similarly, the analog of this in quantum mechanics is that whatever stories that are going on inside, don't worry about them. Just carry out the calculation, find the result, go to the lab, make the measurement, and that is all you need to know about that system. So Copenhagen interpretation is therefore epistemologically heavy. Epistemologically heavy meaning that all it cares about is what you can know, not what is actually there. Okay? And therefore, superposition to it is an interesting mathematical thing. And that's all it is. So physicists have been fighting each other over this for 100 years. There was a time it was famous to do what you call shut up and calculate. Just keep quiet about the philosophy, just do the math, get the results, get your thesis, get your Nobel Prize. The rest of the things are not interesting. But right now, it has become increasingly interesting to think very carefully about what quantum mechanics is telling us. Now, physics education quickly. I think that I used to think that the physics education we were given is poor, and I still do. I think it's wrong to like teach African high school students how doors move, and they're like atomic bombs and nuclear reactors. And by the way, there's something I've not talked about in quantum mechanics called quantum retrocausality, where a particle can influence its earlier state. That is, it can effectively propagate information back in time. There are all these interesting things that are happening in physics, and you're teaching me how doors turn. I don't think it's an interesting way of teaching physics. So I would really love to, if I was some dictator, I would really love to completely reformulate physics education, teach people how to think rather than, how doors turn. So, however, is it useful to like suspend certain forms of thinking very, very early in physics education? I will say not. I think it's important to like understand how doors turn, because it is a simple way of learning how to apply logic in the real world. It's like trying to teach, like I tried today, to teach quantum computers before you have taught computing. It is very, very difficult. So all these foundational things are very important, but it would be important to rapidly improve the coverage of quantum mechanics, relativity, cosmology, astrophysics, high energy physics in high school education. Definitely. We are being undertaught physics in Kenya and probably in East Africa. Another question? We are already 17 minutes out of time. So one final question, and then I have to hand over to Shannon. One final question. Yes, Bernard. Bernard, go ahead.
Hello. Can you hear me? Hello?
Bernard, we can't hear you, sadly. Can you try
Just a minute.
raising your voice?
Can you hear me now? Okay, nice presentation, Carrington. Mine would be to just get an explanation, maybe how we see maybe in classical like computers, we have the way they represent the ones and zeros is from transistors, and then they are arranged in logic gates, and then that's how you get the ones and zero. So for the qubits, I would like to know how it happens, and also maybe to know whether you use do you use electrons, do you use light to get to the qubits?
Karaba, that's a very good question. So first, the problem with, and I think this is a problem also, by the way, in classical computers, it's only that we happened upon a particularly good implementation of this with semiconductors. Okay, the representation of 1 and 0 states. You remember they would use these vacuum tubes. These vacuum tubes were very bulky, and because of that, classical computers like the electronic, numeric integrator and calculator, these were very, very bulky systems until I think there were people at Intel. Somebody correct me, somebody Google this for me. Shockley, etc. Shockley and Badin came up with this semiconductor system that we use. And essentially, all refinements, all semiconductors, and the concurrent Moore's law are as a result of this optimization. So what ended up happening in the history of classical computing is we came upon a particularly good solution. That is my interpretation, at least, okay, of semiconductors, silicon doped, doped silicon semiconductors. So in the case of quantum mechanics, I would essentially say it is not clear that we have an optimum way, engineering-wise, of representing qubits. So that's why we are trying all these things. There is something interesting called topological quantum computing. We will talk about these things later on. Somebody else will talk about these things later on. But essentially, we have not gotten to the semiconductor level, or we have not gotten to the semiconductor state. So if you look at Google's quantum computer, if you look at Windows quantum computer, although there are some principles that are shared, for example, they need to be very, very cold, so that they don't vibrate, so that if they don't vibrate, the chances of them collapsing into a classical state are low. Because of this thing, very many different research groups, research labs, research companies are trying very many different things. Maybe one of them will work and will work at a very simple and cheap and efficient state, such that it will become the standard way of doing quantum computing. But we have not yet reached that stage. So we are still stuck in trying to figure out how exactly do you engineer a quantum computer in a manner that is cost effective and efficient. Your second question, I've totally forgotten it.
Okay, the second question was in regards to, do you use electrons, do you use light? And also because some of us have not been advantaged to go into those practical sessions at the labs, how do you get to get to like trap like one photon or one electron?
Good question. Good question. So, to your first question, use all of these things that you have mentioned and more. There are people who are thinking about using like what are these things? Superconducting quantum interference devices, QUIDs. So there are people like building weird quantum systems and then trying to use these quantum systems in a quantum computer. Okay, so the idea is I want to represent my bits. Okay, my bits are stable. Now, how do I compute? And the engineering details depend on the medium you choose. If you choose a nucleus can be a unit of qubit or quantum computation, the results will be different from when you choose a photon. Okay, your engineering stack will be totally different. Now, how do you track these systems? You essentially use electric fields. So electric fields, or even sometimes you use like physical walls in the case of photons, okay? You use physical walls and you try to like channel them. The one I'm most familiar with is electrons, because electrons can be manipulated using electric fields. So you could create something like a wall like this using electricity. How do you do that? You create a negatively charged wall, okay? And you put an electron there in the middle. This electron is going to be trapped, sort of. Now, because of quantum tunneling, for every 100 electrons you try and trap this way, maybe 2 or 3 will escape. But you could end up with quantum states that are stable there in the middle, which you can now use to build your house, which you can then use to do quantum computing. Okay. In case there are any other questions, I will leave my email in the chat. Please feel free to reach out to me. Those of you in Nairobi, I'm in Nairobi. I'm very cheap, a coffee and mandazi, and then I'll tell you all of these things. So thank you very much. I'll return it to Shannon.
Okay, thank you so much, Carrington. I think just one last question. I see in the chat we have someone who's asking on the implications of quantum computing on encryptions and cryptocurrencies. So maybe a 30-second answer.
So this like needs to be totally unpacked. It's a very complicated thing. So first, somebody needs to understand encryption, needs to understand the encryption technology behind blockchain systems, which then underwrite cryptocurrencies, and to understand whether you could like carry out the effective of a majority attack on a blockchain system without necessarily having majority control of the system. Okay, so this needs to be like completely unpacked, and probably the research on it is not very clear. But the principle is this: if you have protected your systems, like for example, I don't want to speak about cryptocurrencies in particular, but the effective, the generalization of a cryptocurrency wallet, you would call this a node of the blockchain system, okay, or a slice of the blockchain, okay. If you have encrypted this using classical systems, then they are subject to attack by quantum computers. And therefore, the security of blockchains should not be taken for granted if somebody has developed a full-scale fault tolerant is about noise management, fault tolerant quantum computer. Do not take this for granted. It needs to be proven. I think at the Indaba, there was discussion about Apple introducing quantum robust encryption schemes that are robust to quantum attacks. And I would suspect at some point of the entire blockchain ecosystem that such robustness needs to be figured out. Now, how it affects the computation of the blockchain, I do not understand very well. Whether quantum computers will help with the computation of the blockchain, I do not understand very well. Thank you.